All right, local extrema. If you can remember back to Calc 1, we had local max and local min. Local max was kind of like the top of a hill. Local min was kind of like the bottom of a valley. That's all. Same thing goes here, except now we're in 3D. So these are the actual definitions. I don't want you to worry that you know the formal definition. You just have to understand the concept. A local minimum means we are at a minimum point relative to all the points around us, right? So it's sit at the bottom of like a paraboloid, right? Would be a local min. So we can kind of vision, we can get an idea of what it is. Or sorry, a local max. I'm doing these in reverse order. Local max would be like the top of a hill. Local min, bottom of a pit. Pretty much the same definitions from single variable calc. You remember how you found local extrema back in Calc 1? The derivative, set it to 0 and evaluate those critical points for possible extrema. That was it. And we had a first derivative test and a second derivative test. This is going to be pretty similar, except now we have to set our partials equal to 0. So basically we have to set our gradient equal to the 0 vector and solve that system. That gives us our critical points. And we no longer have a first derivative test, but we do still have a second derivative test, which we'll talk about in a little bit. So a critical point is basically a point where the gradient is 0 or undefined. Because if the gradient is 0, we're at a place where the rate of change is not changing. We can use those same analogies from Calc 1. It's where something goes from going up to going back down. Well, there's that instant where it changes. Now it's the same idea, except now it's in the X and the Y direction. It's not changing. So it's actually not too hard to find, well, I want to be a little bit careful about that statement. The idea of finding critical points is not too hard, because what we're going to do is we're going to take our partials. We're getting good at doing partial derivatives, right? Take your partials, you set them to 0, and you solve. Now, the only reason I don't want to say it's always easy, you can, depending on your function, you can get a pretty messy system of equations that, may be hard to solve by hand. Now, here's what we'll actually look at a way of doing it with Wolfram alpha. Okay. So we're going to do a couple examples now that I have a marker that works. So here's what we're going to do. Let's find our partials. So, and let's just find all 4 of them, right? Okay, so f sub x. What is f sub x? Okay, 6x plus 2y plus 7, right? Not too bad. Again, the partials, just as we know, they're gonna be as messy as the function is messy. So these can get really messy, right? I'm not gonna give you a messy one on the in-class part of the exam, but you might get a messy one on a take-home problem, or you might get a messy one in more, and we'll talk about how we can handle that with some help. All right, what about f sub y? Let's deal with f, and then we'll go to g here in a second. So what you do next is you set your partials equal to 0, and you do whatever you need to do to solve. Because what we're going to have is a system of 2 equations with 2 variables, which is what makes it solvable. If we had a function of 3 variables, we'd have 3 first-order partials. So we'd have a system of 3 functions and 3 variables. So a whole bunch of different ways to solve this, but one other way of looking at it, 6x plus 2y equals minus 7. 2x plus 2y equals 8. Okay, I'm just bringing the constants over. This should start to look like an algebra problem, right? Elimination, substitution, whatever you're comfortable with. All right. Now let's do this just for fun. Well, actually, let's do both. Let's do it real quick. This is set up perfectly for elimination, right? Because we can eliminate the y's. So 6x minus 2x is 4x, 2y minus 2y is 0, -7 minus -8. So we get x equals -15 over 4. We can plug this back into either equation to get our y value. So it doesn't matter. Okay, let's take the first one. -15 over 4 plus 2y equals -7. So what do we got? -90 over 4 plus 2y equals -7. Since we're going to be dealing with fractions, let's reduce this. So -45 over 2 plus 2y equals -14 over 2. Very good. So add 45 over 2 to both sides. Sorry about writing at the bottom for you guys at home. 31 over 2, I like it. So we got 2y equals 31 over 2, or okay. So let's just say we get a nasty one. All right. Could be on the homework, could be on a take-home problem, or just a problem that you're working on. You know, when you're at home, use the tools available to you. We know what the answer should be. So Wolfram Alpha is pretty flexible. So I just do something like solve. What did we have at the? And you can go right off the beginning. So 6x plus 2y plus 7 equals 0. Let me know if I put anything in wrong. 2x plus 2y minus 8 equals 0. So and that answer looks very familiar, right? So you're gonna know if it's something like this, doing it by hand is probably actually quicker than calling up Wolfram Alpha. But if you get something with some, you know, where the x's are in the denominators and you got a y squared and a bunch of mess going on. Yeah. Yeah, and if it's a linear system, you could always use the matrix in the calculator. If it's a 3x3, you know, use technology.
Oh, no, stop. God.
Sorry?
Sorry.
I don't think that was directed at us. Here's an excellent. Okay. All right. So those are our critical points. So we have one at the point -15 over 4, comma 31 over 4. Let's take a look at what's going on graphically. We'll look in a little bit about how we do it analytically. So give me just a sec because I need to switch a couple things. So here, we're gonna be over here now. Maybe. There we go. All right, so here's a plot of our function. All right. So we can see that it has a minimum, and if we look at where that is, the y is positive, the x value is negative, just like we would expect, right about where we were looking. All right, there's a couple, so we can see that this place is a place where our gradient is 0 down here at the bottom. Now, a couple things I want to look at. I'm going to do a contour plot. And we'll start down there. And I don't think that should be it. Oops. And when we do a contour plot, And we're also going to add our, oh no, we're not doing a constraint, sorry. All right, here's our contour plot. I did not do what I wanted to do. Let's try that again. Okay, there we go. Hang on, give me a sec to zoom out. All right, remember that we know that our min, right, -15 force is just a little bit less than -4 in the x. So that's right there. And 31/4, that's just a little bit short of 8 in the y. So right there's our critical point. What I want you to notice is what the contour lines look like, right? And we looked at this when we looked at contour lines. We saw that when they were concentric circles or ovals, they tended to make a max or a min. So we can identify the type, that whether or not we have a max or a min, by looking at the contour plot as well. Because we would see those concentric circles, and here's exactly why. Is now we see the, or I guess they're more oval shaped, but we can see them actually on our 3D plot, right? So gives us an idea of, contour plot can give us an idea of what we would be expecting to see. Questions at this point? So what I'm trying to do is give you multiple representations of the same thing, so that when you go to work problems, you can get an idea of what it is you're looking for and what they look like, right? So from a contour plot, we can tell if we have maxes or mins. So we're kind of matching the algebra to the geometry. All right, so I want to leave this up here for right now, and I want to bring up the other one. So our g of xy, which I think this system even works out easier. So what's g sub x? All right, so one of the things that makes this system so easy is this only has x in it, this only has y in it. So these are basically just linear equations, right? You set them equal to 0. Well, up here, you're going to get x equals -3. And here you just get y equals 1. So we've got a critical point at -3, 1 for g. Great. Let's see what g looks like and how we can make sense of it. All right, so here's a plot of g. And if we look, we said we had a critical point at, what was it, -3, 1. So let's see, zoom in a little. There's -3 in the x. And there's 1 in the y. See that little yellow piece right there? That right there is where our critical point is. Now, it almost looks like a min of this valley, but this valley is actually outside of our graph. If I spin it this way, it meets a peak. So what kind of critical point do we have? We have a saddle point. Notice how it kind of looks like a saddle. It's neither a max nor a min. So this is a saddle point. And I want to show you what the contours look like on this guy. Right there's our critical point, -3, 1. See how the contours kind of make an X? They don't have that concentric circle look anymore. In fact, if we move if I move these down a little, let's do this. Let's do -5, and we'll add a few. You'll see it kind of has a look. Oops, I didn't want to do -51 there. kind of looks like a double hyperbola and has this X shape. Well, if we spin our graph, you can start to see why. Because we basically have the intersection of two hyperbolas. So once again, saddle points can be recognized from a contour plot. It'll be very distinct. It'll have this X-shaped pattern that you're seeing on the side. All right. So those are the types of critical points we're going to see: maxes, mins, and saddle points. Now we know how to identify them graphically. Let's talk about identifying them algebraically, which is the second derivative test that you saw in the video. I'm going to go through where the second derivative test comes from, but that's not something you need to worry about. I just want to give you some of the logic behind it. We just need to know how to use it. And remember, on the midterm, you got two note cards. You definitely will want to put the second derivative test on there. Do not try to memorize it. All right, I don't even have it memorized for multivariable. So let's take a look at the second derivative test. And then we'll run the second derivative test on one of them. We don't need to do both, but we'll do one of them, whichever one we decide we want to do. All right. So if you can remember back to Calc 1, there was a second derivative test, but most of the time we use the first derivative test. But where the second derivative test comes from is basically a second degree Taylor polynomial. Second derivative test for Calc 1, for single variable calc, basically all we look at is the sign of the second derivative, because if the second derivative is positive, we have something that's concave up. And I don't think my annotations are still working today. Yeah. We have something that's concave up. And if something's concave up, well, the critical point sits at the bottom, so we'd have a min. If we get a negative in our second derivative, it's concave down. Concave down would have a critical point at the top and hence a maximum. So we're going to use that basic same idea when we derive the second derivative test for multivariable calc. Now, one problem with the second derivative test in Calc 1, if the second derivative is 0, it's inconclusive. And we will have cases where the second derivative test is inconclusive in multivariable as well. All right, so a basic quadratic is given by in two variables is ax squared plus bxy plus cy squared. So we're just going to let 0, 0 be a critical point to simplify things and build this test. All right. I wish I could annotate on this, but I want to talk a little bit about what I'm doing here. Let's at least get the. So basically, all I'm doing is completing the square. So what's going on inside these parentheses? I added in this term because I want a perfect square inside the parentheses, which is why I had to subtract it off out here. Now, this term that would have been a squared gets multiplied by this a to get out of these parentheses. That's why there's no a squared here, but the 2 you can see is squared to be the 4. The b is squared, the y is squared. All right, so this is completing the square. This is college algebra. This is just some algebra. Now, that made a perfect square on the first part. So I rewrite it as a perfect square. On the second part, I factor out the y squared to get this c minus b squared over 4a. All right. Again, you know, if you ever want to see it, we can always find a YouTube video on it. So just email me if you can't find one. But it's just completing the square. And now we're rewriting things to put them in a form that'll be more usable for us. All right. So first term is still the same. Second term, what I'm going to do is give a common denominator so that I can write it all over the same denominator. For ac minus b squared. Now remember what a, b, and c are. Those are the coefficients of the second degree multivariable function. Okay. This will all look like what you saw in the videos shortly. So here's where we're at. A is getting multiplied by the x squared term. This thing here is getting multiplied by the y squared term. So let's talk about this. If A is positive, that means the x squared term would be positive. Remember what positive means in a quadratic, it means concave up. So we're concave up in the x direction. Now, if 4ac minus b squared is also positive, so that's this numerator here, and remember we said a is positive, so positive over positive is positive. That means the coefficient of y squared is also positive. So that means we're concave up in the x direction and in the y direction. That gives us a min at the bottom. Okay? And it's all about the concavity. If a is less than 0, so now a is negative, that'd be concave down in the x direction. And we had this 4ac minus b squared positive. Well, it's being divided by a negative, so positive over a negative is negative. That means concave down in the x and y direction, we get a local max. If a is greater than 0, and now this 4ac minus b squared is less than 0, what happens now is, because this is positive, concave up in the x direction, we have a negative over a positive, which is negative, so concave down in the y direction, that's where we get our saddle. Very similar, this will be a saddle as well. Now I'm going to simplify this, so don't feel like you have to, this is going to get cleaned up. All right, because we have to put this back into our notation. If the 4ac minus b squared equals 0, that's our inconclusive case. All right. That's what's going on. I just want to give you some intuition as to where this test comes from. And it's all about concavity. Now, looks messy. This is a second degree Taylor polynomial of a multivariable function. It involves the first order partials, the second order partials, and the mixed partials. Well, we only care about the quadratic terms, all right? We only care about the concavity at the point because all we're doing is testing for a max and min, so we can not worry about the rest. Remember, I'm lining this up with that ax squared plus bxy plus cy squared that we looked at before. All right? So the A is based off of f sub xx, the B is based off of x sub xy, and the C is based off of f sub yy. This is where everything's going to get cleaned up in terms of our partials. And remember, we only care about the sign of A and B and C. We don't really care that much about the value. So the fact that it's over 2, we don't worry about. But here's how this is all going to clean up. That 4ac minus b squared, when I plug in the a and the c in terms of the partials, the 4 is going to cancel out with these two 2's. And this is where you get your second derivative test that you saw in the videos before class. This is called the discriminant. For those of you guys who remember the quadratic formula, b squared minus 4ac was known as the discriminant. Look familiar? It's amazing how things always come back around. It's like a boomerang. All right, here's the best part. This thing's actually really easy to use. Okay, I just, I went through that stuff because I wanted you to know where it came from, because I wanted you to see the idea of the concavity giving us maxes and mins. But all we need to know is what the discriminant is and what the conclusions are. So if the discriminant is positive and f sub xx, which was our A, is also positive, we have a min. If f sub x is negative, we have a max. And if the discriminant is negative, we have a saddle point. Finally, if the discriminant is 0, we do end up with our no conclusion case. And as we just discussed a couple minutes ago, what we do if we have one of those where we can't draw a conclusion from our second derivative test, we'll go and evaluate that critical point graphically. We'll just graph our surface around that critical point and we'll see, is it a max min saddle point or it could be none of the above. This test could have been done if we had completed the square for y, but we decided to we conventionally complete it for x. So that's why we get what we get. All right. Let's see this thing in action. Let's just do it with f. All right, so what you need to do is you need to find the discriminant, which up there is f sub xx, f sub yy minus f sub xy squared. All right, so we need to fill in this discriminant. D equals f sub xx times f sub yy minus f sub xy squared. So we need our mixed order partials. All right, so f sub xx, well, pretty easy one, right? Just 6. F sub yy, 2. And f of, remember, these are equal, f of xy or f of yx, so it doesn't matter which one you find. So f of xy is going to be 2, or f of yx is going to be 2. Now, I want to point out, in this particular case, all my second order partials came out to be constants. They don't have to be. They could be functions of x and or y, in which case you plug in the critical point for x and y to get what they are, okay? So you should be plugging in constants to your discriminant, because remember, we're doing this at the critical point. So we have 6 times 2 minus 2 squared. So 12 minus 4, which is 8. Our discriminant is positive. F sub xx is positive. Based off of our second derivative test, we've got a local min, which is exactly what we saw when we looked at it graphically. All right. So that's how you use the second derivative test. It is very straightforward. It should be something, one of the things you definitely put on your note card. So that's the second derivative test. It is very straightforward to use. We know how to find partials. So let's review our steps. You find your gradient, you set your gradient equal to the 0 vector and solve. That gives you your critical points. Then you apply your second derivative test using your second order partials with your critical points plugged in. So if you have more than one critical point, you'll reevaluate your second order partials at each critical point. All right. Again, they won't always end up being constants. Questions about the second derivative test? All right. I think you're going to find it straightforward to use. And again, once you get better and more comfortable with partials, it becomes easier to do. All right. We are going to talk a little bit about some constrained optimization. We had something called the extreme value theorem that said if we had a function on a closed bounded interval, we were guaranteed both a global max and a global min, either at a critical point or at an endpoint. All right, now that was actually one of the easier things in Calc 1, because all you had to do was find your critical points and then evaluate your function at the critical points and the endpoints, see what the biggest and what the smallest was. We have something similar, oops, wrong direction. We have something similar in multivariable calc. The only problem is now we're not on an interval, we're on a region. So it does make things a little bit more complex. We're going to look at a couple different ways of handling it. So, now we're going to talk about global max and global min. And there's nothing crazy going on here. Global max means that it is the largest function value on our given region. Global min, smallest function value on our entire region. Okay. Well, we need some common terminology here. So this is some random region in the XY plane. Doesn't matter what the region is. I just want to give some terminology. So R is the region. P is what's called an interior point. Q is what's called a boundary point. So when we optimize a function on a closed bounded region, once again, we're guaranteed an absolute max and an absolute min, and it'll either incur at a critical point, which would be an interior point, or a boundary point. So we're going to talk a little bit about what's called boundary analysis. But there's a little terminology for it too. It has to be closed and bounded. So R is closed if it contains all its boundary points. R is bounded if all of its points lie within a sufficiently large radius. So it has to be both, and I'm going to give you some examples to make sense of what the difference is. So it can't stretch to infinity in any region if it's bounded. So an example, here's our most favorite case is closed and bounded. The disk x squared plus y squared less than or equal to 4 is closed and bounded because it lies within a boundary and it includes its boundary points. The first quadrant, if we did x is greater than or equal to 0, y is greater than or equal to 0, is closed because it contains its boundary points, the x-axis and the y-axis, because of the equals. But it's not bounded because it stretches off to infinity. If I remove the equals from our example earlier, our disk is now bounded, but it's no longer closed because we no longer are including the endpoints. This is that game where if you pick something closer to 4, 3.999, I can add another 9 to it and I can get a little closer. We can always get closer to that edge without ever reaching it. So that equals, just like in Calc 1, makes a big difference as far as our guarantee. And if we did something like the upper half of the plane, it's neither closed nor bounded because it does not include its entry point, its boundary points, which right off the bat, you can kind of see if you don't have the equals there, it's not going to be closed. And if it stretches up to infinity in any direction, it's not bounded. Most of the ones we're going to look at in here will be closed and bounded. So here's our extreme value theorem for multivariable functions. Like I said, we're going to look at a few different cases of this. So f of x is a continuous function on a closed bounded region, right? That means we're guaranteed a max and a min. And we have to look at two things: the critical points that are on the interior of the region and the boundary points of R. What makes this more complicated than Calc 1? In Calc 1, we only had to check the endpoints, and there was a point on each end. Now, as you can imagine, checking boundary points, well, there's infinitely many points in the boundary. So we have to have a way of checking the boundary region. And I'm going to show you a couple different ways in a couple examples. Okay. So here's our first one. And I want to show the graph of this because I think it's kind of cool. So this is done in a program called Maple. You guys actually do have access to Maple. There's instructions on how to get into it in the midterm take-home problems if you ever want to decide to use it. You don't need it. Everything we do in here can be done with all the other stuff we've looked at. But if you ever want to mess around with it or try it for some other stuff, you can. There's a particular plot that I can only get to work in Maple. I can't do in Calcplot 3D, and it's what's going on with this. So what we have is we have a plane, 10 minus x minus 2y, and then we have a region that is this triangle in the xy plane. So first off, I just want to give you a visual of what we are looking at. And then we'll match it up later. So don't worry about the code. Like I said, if you ever want it, just email me and I can send it to you or upload it. So here's kind of what's going on with the function. We're gonna see what's happening here in a little bit. So this is saying there's an F max of 10 and an F min of -1. We're gonna verify that here in a second, but here is what's going on. So what we have is this triangular region in the XY plane. This is the black outline here. And that cuts out this triangle on our surface. All right, let me give you the full surface and so you can see it even a little better. So this grid here, that's our plane. This is the triangle that's in the XY plane being projected on our surface. So our max is right here. And our min is a little harder to see on this one. Let me see if I zoom in a little bit. Oh. Actually, let's do this. That min is going to be down here. Now you can see a little bit better on this graph. Oh, there's that max of 10 that we saw before. There's that min, and you can see how it's below, you know, this is the XY plane right here. So it's a little bit below the XY plane, that -1 we were seeing before. Well, that's all well and good, but I just showed you that Maple, a program we've never used in here before. So how do we see that that max is 10 and the min is -1? There's a couple different ways. Well, first thing you do is you run your second derivative test because we're going to look for critical points. Okay. So that's still going to be our first step, which for this one, f sub x equals -1, f sub y equals -2. There's no way to get those equal to 0. So no critical points. So we don't have to worry about critical points, but we're in a closed bounded region. So we're guaranteed an absolute max and an absolute min. They're just going to lie on the exterior. Okay. Couple different ways of going about that. What we're going to do in this one is we're just going to use the fact that they're straight lines and that the relationship between x and y is constant on each of those lines. That's one option. Another option is to parameterize the region, the boundary, and that will make your function a single variable function. All right. I'm going to do a second example where we parameterize. So you're going to get a chance to see both. So what we can do is if we look, well, notice when I'm on L1, so specifically when I'm on L1, my y value is 0, right? So what am I looking at? I'm just looking at f of x comma 0, which is going to be 10 minus x minus 0. And x, as we can see, is going from 0 to 5. Now let's do this. Now this is linear, so we're not going to spend a lot of time on this, but if this weren't, guys, this is a single variable calculus problem. We're on a closed bounded interval. This is guaranteed max and a min. You find the derivative, find your critical point, check your function at your critical points and your endpoints. The derivative is -1, so there's nothing to check there. So all we do is we check f of 0 comma 0, which is 10, and f of 5 comma 0, which is 5. All right, so that's our max and min on L1. And we'll do the same thing for L2. Notice on L2, x is constant, right? X is always 5. So now we're looking at f of 5 comma y. So we have 10 minus 5 minus 2y, which is 5 minus 2y, and y is going from 0 to 3. So once again, we have f of 5 comma 0, which is 5, and f of 5 comma 3, which is -1. Starting to see those answers that we saw in Maple show up. All right, L3. Now X and Y are neither constant, but they have a constant relationship. Specifically, they're always going to lie on this line. We have a rise of 3, a run of 5. So basically, when we're on L3, y equals, when we're on L3, y equals 3/5 x. All right, so this is one way of handling boundary analysis, is if you have one of them as a constant, you just put it in and you're down to a single variable, or you find a relationship between your two variables and say, okay, well, y is equal to x squared when I'm on this part of the curve. So you sub it in. So we have f of x comma 3/5 x. So we have 10 minus x minus 2 times 3/5 x, which we'll simplify to 10 minus x minus 6/5 x. So 10 minus, let's see, 5/5 minus another 6/5, so minus 11/5 x. And we can see here, x is going to go from 5 down to 0, or 0 to 5. So when x is 0, we're going to get 10. So when x is 0, it's going to be basically x of 0 comma 0. And when x is 5, we're going to get 10 minus 11, or -1. So what we're doing is we're analyzing it on each part of the boundary. Because we don't have a nice continuous curve, we actually have a triangle. This could be done via parameterization. What you would do is parameterize each of these lines, plug in your parameterization to the function, and do your calculus on each segment. All we do now is identify the largest, right there, the 10, that's our max, and the -1, which happens in a couple places, is our min. All right, that's one way of doing boundary analysis, especially when you have one that is made up of piecewise continuous curves. You have to do each one separately. There's no way to do it all at once. Questions about that one? Okay, let's do one more. This one I will do via parameterization, just so you can see what that looks like. I'm not going to worry about that slide, but here's the other one we're going to do. This will be the last one. So we're optimizing x squared plus y squared on the region below, which is a circle of radius 3 centered at 1, 0. All right. So I got a plot of this one so we can see what it looks like. All right, so basically we have our paraboloid. And what we can do is we can add in our constraint curve. All right, I'm going to add it in parametrically. These are the parametric equations that create that circle. All right, this is just trig. The 3's are what give it a radius of 3, and then I shift it right by adding 1 to the x coordinate. So this is something you can do in Calculate 3D under the contour plot menu. And so now look at what we see. We see the contours of our function, and the blue is our constraint. Okay. Now, this is kind of cool. Once we go into 3D, we are looking for a max and a min. Now, the green is our circle in the XY plane, but you guys see the blue okay? That's our constraint projected onto our surface. So now remember, we're just looking for the min and max on our region. So we have a max right up in here, because that's, that's the end of our region right there. So that's going to be our max, which does it look like about 16. And our min is actually down here at 0, 0. Now, if our constraint had been just the edge of the circle and not the entire region, then our minimum would have been over here. All right. And that's something we're going to see in Lagrange multipliers. And we'll look at it today too. All right. So this is going to be cool. We're going to go through this. This is going to be a nice little walkthrough of everything. And it's not a bad function, so it won't take too long, but it allows us to refresh the steps. All right, the problem is to optimize this on the given region. So we have the function g of x, y equals x squared plus y squared. And we're on this circle. So a very easy way to optimize it is x of t equals 1 plus 3 cosine of t, and y of t equals 3 sine of t. Now, we do I shouldn't say different things. We have two steps here. One is the optimization we were doing earlier, which is finding maxes and mins. So that involves getting our partials. G sub x is 2x, g sub y is 2y. Setting those partials to 0, solving that system. We very clearly have a critical point at 0, 0. All right, next thing we do is we would test that critical point in the second derivative test. Well, look at what's going to happen. In this particular case, we'd have our g sub xx equals 2, g sub y equals 2, and g sub xy equals 0. So our discriminant is 4 minus 0, or 4. So we get a positive discriminant. And our g sub xx is positive, which means concave up, means we have a min. We saw that in the graph. Again, I just want to bring it all together so that, when you're working a problem, you go through all these steps. So we know that 0, 0 is a min. One thing I didn't mention, when you get your critical points, we only need to test critical points that are in our region. So if we had gotten a critical point out here, like at 4, 0, we would not need to test it because it's not inside our region. 0, 0 clearly is, so we need to test it. All right, next comes the boundary analysis. What we're going to do is we're going to rewrite G in terms of T. So let's do that in a separate color. So this is going to become a G of T, which is 1 plus 3 cosine of T, the quantity squared, plus 3 sine of T squared. We'll multiply this out, which is 1 plus 6. This has to be FOIL. You can't distribute the square. Remember that. 1 plus 6 cosine T plus 9 cosine squared T plus 9 sine squared T. Guys, this is now a single variable calculus problem because we just have a function in terms of T. And we've got a Pythagorean identity here. So 9 cosine squared plus 9 sine squared is just 9. So that's 10 plus 6 cosine of T. And we're looking for the max and min here. So again, we're in single variable calculus. Our T, we're just going around the circle. I should have put it up here with the, is between 0 and 2 pi. But this is an easy one to do because cosine, the smallest it is -1, biggest it is +1. So the biggest we're going to get is at g of 0, which is 16, which we saw in the graph, right? And the smallest we're going to get is at g of pi, which would have been our critical point from here, which is 4. So, remember what we wanted? We wanted a global max and a global min. We can see it clearly now. That's our global max. This is our, sorry, I know the red's not going to show it very well at home, is our global min. This would have been the minimum if we were only doing if we were only on the boundary and not inside the region as well. But because we're also including inside the region, we had a point in there that goes lower. It did not occur at a critical point. What that is, if we come back over to the graph, that's this point here, and it just happens to be the lowest point on the boundary that's on our surface, but it doesn't qualify as a local min because it's not lower than the points around it. You know, we have some points over here that are lower. It doesn't have that bottom of a cup or bottom of a bowl look.
Okay.
It's a good clarification.